Distributed Systems from Scratch. This is episode 22, How to Read Papers and How to Find a PhD Advisor. The series finale. 21 episodes taught you distributed systems. This last one teaches you how to go further on your own after the series ends. How to read the primary sources, how to find the right mentor, how to decide whether the research path is for you. This is the bridge from being a student of the field to becoming a contributor to it. Why bother reading papers when blog posts exist? Blog posts summarize, textbooks simplify, documentation describes the current state. All of them are filtered through someone else's understanding. Papers are different. Papers contain the original reasoning. Why did the authors make this choice? What alternatives did they consider and reject? What are the real limitations they're honest about? Every system in this series, Pexos, Raft, GFS, Bigtable, Dynamo, Spanner, Kafka, Flink, was first described in a paper. The paper is the source of truth. Once you can read papers, you can learn anything in this field without waiting for someone else to summarize it. There's a classic technique for reading papers popularized by Srinivasan Keshav, the 3-pass method. Pass 1 is the skim. 10 minutes. Read the title, abstract intro and conclusion. Glance at section headings and figures. Your only goal is to answer, what problem, what approach is this relevant to me? After pass 1, you decide if pass 2 is worth your time. Pass 2 is the understanding pass, about an hour. Read fully, study the diagrams, follow the logic, skip the proofs. After pass 2, you can explain the paper to a colleague. Pass 3 is the critic, 3 to 5 hours, sometimes more. Rederive the design yourself, challenge every assumption, read the proofs, check the evaluation methodology. After pass 3, you could review this paper for a conference. Most papers deserve only pass 1. A few deserve pass 2. The classics, the ones that shape your field, deserve pass 3. Here's the anatomy of a typical systems paper. The abstract gives you the problem, the approach, and the result in one paragraph. Read this first. The introduction explains it. Motivation, contributions, roadmap. This is where the authors tell you why you should care. The design or architecture section is the meat. This is the core contribution. When you do pass 2, this is what you study deeply. The implementation section gives you the practical details. What language, what optimizations, what was actually deployed. The evaluation is where the claims are tested. Read this critically. Are the benchmarks fair? Are the comparisons honest? And finally, the related work section. This is gold. Every good paper cites 30 to 50 others. The related work section is a curated reading list for the entire subfield, handpicked by an expert. Follow the trail. When you're reading, 2 mental checklists matter. The good stuff to extract. What problem is actually being solved? What is the key insight or technique? What trade-offs did they accept? What does the evaluation actually prove? And crucially, what did they not solve? The red flags to watch for. Evaluation only against straw men. No comparison to existing systems. The phrase, we leave X for future work when X is actually essential. Throughput numbers measured under unrealistic conditions. And claims of novelty that quietly ignore prior work. Reading critically is a skill. The first few times, every paper looks brilliant. After 50, you start to see the patterns. The rhetorical tricks, the missing baselines, the cherry-picked workloads. That skepticism is part of becoming a researcher. A few rules for building a sustainable habit. 1 paper per week, not 10. Depth beats breadth. A pass. 2 reading of 1 paper is worth a pass 1 skim of 5. Write a 1 paragraph summary after every paper. If you can't summarize it, you didn't understand it. This forces honesty. Follow citation trails. Every paper points to 30 or 50 others. Let the field guide you to its own foundations. And start with the classics, the systems already covered in this series. You know the context. The papers will feel like old friends with new depth. If you want a starting point, here are 5 papers, one per season of this series. For season 1, Foundations, Time, Clocks, and the Ordering of Events in a Distributed System by Leslie Lamport, 1978, where this entire field began. For season 2, Core Protocols, In Search of an Understandable Consensus Algorithm, the Raft paper by Ongaro and Austerhout, 2014, famously written to be read. For season 3, Building Real Systems, the original Kafka paper by Krebs, Narkede, and Rao, 2011, The Log as Universal Abstraction. For season 4, Advanced, the Spanner paper by Corbett and colleagues at Google, 2012, True Time and Globally Consistent Transactions. And for season 5, Research, How Amazon Web Services Uses Formal Methods by Newcomb and colleagues, 2015, Formal Methods at Industrial Scale. 5 papers, one from each season. Read this and you're ahead of 95% of working engineers. Part 2, Finding a PhD Advisor. The most important decision of your PhD, more important than the university name, more important than the city, more important than the funding package. The advisor is the thing that determines whether your PhD years are productive or painful. How do you actually find potential advisors? Start by reading papers you love and checking who wrote them. The authors are your potential advisors. Look them up on Google Scholar. See their other work, their citation count, their recent activity. Check the program committees of the major systems conferences: SOSP, OSDI, NSDI, Eurosys, ATC. The people reviewing those papers are the active researchers in the field. Cross-reference them with universities currently accepting PhD students. Look at the recent PhDs from each group. Where did they end up? Industry research labs, tenure track positions, strong startups. An advisor's track record with their students tells you more than their own publications do. And then email them, but not a generic email. Read 2 or 3 of their recent papers first. Write a specific message. I read your paper on X. I'm interested in Y. Here's a project I built that touches Z. Generic emails get deleted. Specific emails get replies. Once you've found candidates, how do you evaluate them? On Research Fit, are their current research directions interesting to you? Do they have funding for your area? Are they still actively publishing? Check the last 2 years, not the last decade. Are they open to student driven topics or do they assign theses? On mentoring style, how often do they meet with students? Are they hands on or hands off? How many students do they currently advise? 5 is healthy, 20 is a factory. But the single most important rule, talk to their current and former students, not the advisor. The students. Ask them directly what working with this person is like. The good advisors will encourage that conversation. The ones who try to prevent it, that's your answer right there. When you actually apply, 4 things carry the most weight. The research statement. What problem interests you? Why does it matter? And what have you done that demonstrates research ability? Be specific, not generic. Research experience. Publications help, but they're not required. A solid open source contribution, a real systems implementation, a detailed technical blog series, all of these count. The committee is asking, can this person do independent technical work? Recommendation letters from people who know your research work, not just your grades. A letter that says they built X from scratch and debugged a subtle race condition beats top of the class every time. And faculty match. Apply to programs where specific faculty match your interest and mention them by name in your statement. I want to work with Professor X on Y because of their paper Z. Admissions committees read for this. They want students who already know who they want to work with. The research statement itself follows a simple 4-paragraph structure. Paragraph 1. The problem you care about and why. I'm interested in X because Y. Paragraph 2. What you've already done about it. I built ZID. I read these papers. I found this gap. This is where you prove you're not just curious, you're active. Paragraph 3. What you want to do next. I want to explore approach W. Here's why I think it could work. Here's what I'd need to learn. Speculative is fine. Committees no plans change. They want to see how you think. Paragraph 4. Why this specific program and this specific advisor? Professor X's work on why aligns with my interest because their paper Z showed tailor every statement. Generic statements signal generic candidates. 1 to 2 pages, no filler. Specific, not vague. Show that you've done your homework. Step back. Is a PhD even right for you? It's right if you love asking why does this work more than what should I build next. If you enjoy long deep problems measured in years rather than sprints. If you want to push the boundary of what's known. If you're comfortable with ambiguity, with months of work that might lead nowhere. It might not be right if you want the credential more than the process. If you prefer building products to exploring ideas. If you're motivated primarily by salary, industry pays better, faster, and almost always with less stress. If you need structure and clear milestones, a PhD will frustrate you. Both paths produce great distributed systems engineers. Knowing which path fits you matters more than picking the prestigious one. If a PhD isn't right, the alternatives are real and respected. Industry research labs, Google Research, Microsoft Research, Meta AI Research do real research without requiring a PhD. Hard to get into without one, but possible if your system's work is exceptional. Open source contribution. Become a meaningful contributor to CockroachDB, etcd, Kafka, TIKV, RocksDB. Real distributed systems experience visible to everyone with mentors built into the community. Build from scratch. Implement Raft. Build a distributed key value store on top of it. Write a TLA plus specification for something you care about. This teaches more than any course, and it's exactly the artifact a PhD application or a research track job interview wants to see. Now, the recap. 22 episodes, 5 seasons, 1 field. Here's the map of where you've been. Season 1, Foundations, 5 episodes. Why distributed systems exist at all. The two generals problem. Time, clocks, and ordering. The CAP theorem. Consistency models. By the end of season 1, you understood why distributed systems are fundamentally hard. Season 2, Core Protocols. 7 episodes. Paxos and Raft for consensus. Replication. Partitioning and sharding. Fault tolerance. Distributed transactions. Gossip protocols. By the end of season 2, you knew the protocol toolkit that almost every modern distributed system is built from. Season 3, Building Real Systems. 3 episodes. Distributed Storage, GFS, Bigtable, LSM trees, Stream Processing, Kafka, and Flink. System Design Patterns, how the primitives compose into real architectures. Season 4, Advanced Topics. 3 episodes. CRDTs and the Local First Vision, Geo-Distributed Systems and True Time. And the Season 4 finale, Byzantine Fault Tolerance from PBFT to Hot Stuff. Season 5, The Research Frontier, 4 episodes. Formal Verification with TLA+, Distributed Machine Learning, the open problem still driving research. And this episode, How to Read Papers and Find an Advisor. From what is a network to how to push the frontier. That is the complete arc. Step back and look at what you actually know now. The primitives, consensus through Paxos and Raft, replication, leader-based and leaderless, partitioning by range, hash, and consistent hashing, transactions through two-phase commit, sagas and serializable snapshot isolation, failure handling through retrees, circuit breakers and chaos engineering, gossip and epidemic algorithms. The systems GFS, Bigtable, HDFS, Cassandra, Kafka, Flink, Rocks, DB, Spanner and CockroachDB, CRDTs underlying Automerge and YJS, PBFT, Hot Stuff, Tendermint. Distributed training systems like DeepSpeed, Megatron, and PyTorch's distributed data parallel. That's a real toolkit. That's enough to design a system at almost any company in the world. If there is one meta lesson from 22 episodes, it is this. Every distributed system is a composition of the same small set of primitives. The art is knowing which to combine and which trade offs to accept. This was the thesis of episode 15. It is the thesis of the entire series. From the two generals to the Byzantine generals, from Lamport clocks to true time, from crash faults to Byzantine faults. The same patterns recurring at increasing scale and increasing complexity. Once you see the patterns, every new system you encounter becomes legible. So, what's next for you? Build. Implement Raft from scratch. Build a distributed key value store on top of it. Nothing teaches like building. The MIT 6.584 O labs are free, public, and excellent. Read. Start with the 5 essential papers from this episode, one per week. Follow each paper's citation trail. Build your own mental map of the field. Contribute. Pick an open problem from episode 21. Join an open source distributed systems project. Write what you are learning publicly. Teach the next person. The fastest way to deepen your own understanding is to explain it to someone else. Thank you. 22 episodes, from Why Do Machines Talk to How to Push the Frontier of Human Knowledge. If you've made it here, you understand distributed systems at a level that most engineers never reach. You know the theory, you know the protocols, you know the real systems, you know the advanced topics, and you know the open questions. Now go build something. Distributed systems from scratch. Series complete. 22 episodes. 5 seasons. From scratch to the research frontier. Thank you for watching.